Hello, everyone. Congratulations on being accepted to the residency. My name is Shauna Fields, and I'm going to be your virtual Praxis tutor. I have been teaching for 7 years, at the time of this recording, in CMS, and I've taught just about every science there is. I came in to this work through Teach for America, which is a program very similar to the one that you are going to be embarking in. And I remember what it was like having to kind of study and prepare for this Praxis. I did not have a science background when I started this journey, so I'm with you. You're going to go through 8 different sessions geared towards different areas of science. The first 3 sessions are physical science, that's physics and chemistry. We have 2 sessions on life sciences, which is like biology, a little bit of anatomy in there. And then we have some other sessions on geology. There'll be one that talks on like taxonomy, ecology. We'll hit a little bit of some history and the nature of science, just some different areas that are also in the test. Instead of me sitting here talking to you like this, I've actually put together recordings of previous sessions that we did in the 2018-2019 rotation. I felt like it might be a little bit better for you to kind of hear from some people who were already in the same shoes, trying to get ready for the Praxis. They had really good questions, and to kind of learn from them. Feel free to kind of pause the videos as you need and stop and take some notes, take a breather, replay them back. These are here for you to help you pass the Praxis. The first session is one of our longer ones. So the first session that you're about to see is going to be about 58 minutes long. It'll go over some information about the Praxis itself. So how does the middle school differentiate from the high school Praxis? The scores that you'll need to pass. It'll also have, so we'll start talking about chemistry in that one. Pardon me for checking my notes. But we'll talk a little bit about the periodic table. We'll talk about protons, neutrons, electrons, radioactivity, half-life, and types of reactions, and also balancing. So this is a meaty session. Please make sure that you pause it as it goes, take some notes. I believe you'll have access to all of the guides that we use. So all the materials should be in the folder all the materials that we reference should be in a folder for you already. Good luck on this journey, and I hope that these sessions help you, and I hope to be working with you in the summer field experience. Good luck. The question is chemistry based, so if you take a second to read it, and you could answer in the chat box, or if you want to say it out loud, that would be awesome.
79 electrons in a neutral atom.
So I got D. I heard Sam say D. What you thinking, James? Wow, my son is tearing up those toys. Okay. Not a problem. I agree. The answer for this one is D. 79 down there at the bottom is the atomic number, which also means it's got 79 electrons to make it neutral. Excellent. So this seems like this will be a faster section for us to get through. First thing we're going to do, though, is talk about the test. So right now, I don't know who's middle school and who's high school. So if you want to identify that, that also could help me out. They did not
High school.
High school, middle school, and okay. So, geez, this slide is for you. The middle school test is very similar. So the 2 Praxises are very, very similar to one another. They're broken down roughly the same in terms of like the content areas. The only difference is the amount of questions. The middle school test has slightly less questions than the high school test does. So for the middle school test, you have 2.5 hours. You have 125 questions. A passing score in North Carolina is 150 for the middle school test. So that's about 94 of the 125 questions that you want to aim to get, roughly. Their grading scale is a little different. If you look on the screen, you'll see that the biggest part of the test is broken down between basic principles of matter and energy in physical science. That's a little under, like a little bit around what, 436, roughly 40? I'm not doing math in my head right now, sorry. 20 to, yeah,
The basic principles of matter and energy is essentially chemistry. So you're looking at a big portion of your test being chemistry and physics. Physical science is also chemistry and physics. For Sam and Triana, the general science test is still the same time frame, but it's 10 questions longer. Passing score in North Carolina is a 151. So you're looking at 100-ish questions that you're aiming to get correct of the 135. Again, you'll see that 38% of the test is based on physical science. So that's physics and chemistry, a little bit less on the scientific methodology, techniques, and history. So James, your test is going to have more names and people than the high school test will. The high school test, however, is going to have a little bit more on methodology. So like, how do we have chemical safety and scientific method is a little bit more of that in the high school one. I see a question here. Oh, there you go. Good, because my minor was not. My majors were criminal justice and psychology, so I still to this day do not know why I teach science, but we're here. Let's really quickly talk about the pre-work. So I just want to cover the one question that was most missed. And a lot of people who did the pre-work aren't on the call, so I'm also going to do this because I'm recording it to send it out just in case. And the most missed question was this one. It says the number of atoms contained in 12 grams of carbon is what? And a lot of people picked 22.4. To know this question, you would have to know a little bit about the periodic table and about moles, which is a unit of measurement in chemistry. In chemistry, a mole is equal to Avogadro's number, which is 6.02 times 10 to the 23rd particles, molecules, or atoms of anything. So the one thing to kind of get this problem right, you would have to be able to associate 12 grams, which is the molar mass of carbon. So 1 mole of carbon is equal to 12 grams, which means it's also equal to Avogadro's number, which would be here. If this problem had said liters, then the answer would have been 22.4, because 1 mole is equal to the molar mass of something. 1 mole is equal to Avogadro's number, and 1 mole is equal to 22.4 liters. They are all equivocal. It just kind of depends on the unit. So this was the most missed question of our warm-up. And now we have a little explanation as to why. I'm going to start talking about the periodic table a little bit today. As a disclaimer, so let me make my mental asterisk, which I'll probably be making periodically. These sessions are designed to kind of help you with studying, but this should not be your only source of studying and preparing. I don't know, I cannot see all of your diagnostic scores right off the bat. I have to go back and look at them. So I don't know where you guys are, and they'll release to me in probably in a day or so, like how the breakdown of your diagnostics, so I can see where everybody is. But please don't let these 8 sessions be the only form of studying that you do. The tests are so big and so expansive that they do require a good amount of studying, especially if science is not something that's like right in your prefrontal cortex right now. Okay. So let's just start reviewing real quickly. I'm just gonna briefly kind of go through some concepts with the periodic table. We'll spend a little time talking about atoms, isotopes, and ions. And if we have time, we'll get to some radioactive decay and nuclear half-life, which is a lot of stuff. But my hope is if we're pushing and if you guys are okay, we'll just get to the end. And if there's more questions, we'll wrap them up then. Also sent out the notes for this lesson already. So if there's something that you want to like write down, you can write it on paper, or you can print those out later and add it to, but I sent them out in the second reminder email for this evening. So let's look at our good friend, the periodic table. The nice thing about the test is that you will get a periodic table. So this is a great help to us in the physical science section. They're going to give you a small reference table, but the biggest part of it is going to be our periodic table friend here. If we know how to read it, a lot of the physical science stuff becomes a lot easier. So real quick to get us started, let's just talk about how this thing is organized. For some of us, this will be review. For some of us, this might be slightly new. Okay. So on our good old friend, the periodic table, the first way it's organized is by period and by group. We have 7 periods, so those are the rows across. Please note that the lanthanide and astenide series really kind of fit in right here. So some people will be like, oh, there's 9 periods. There's 7. These bottom 2 rows that are pulled out fit right in between. The good thing about our periods is that the periods tell us our shells or our orbitals. So with us having 7 periods, if we had to draw Bohr models, which luckily the test does not really ask about, Bohr models go by, you draw like a little circle to represent the nucleus, and then you have some outer rings. Whatever period you're in is how many rings that you draw. So an element that's in the 5th period would have 5 rings, whereas an element in the 2nd period would have 2 rings around it. The rings are called its radius. So that means the farther down you are, the bigger your atomic radius. Okay. The other way the periodic table is organized is by group. So we have 18 groups or 18 columns on the periodic table. All the ones that are colored, we call these the A group. So this would be family 1A, this 2A. If we counted this out, this yellow column would actually be the 13th family, but we call it 3A, then 4A, 5A, and so on until we get to 8A. The reason that we have the A group is the reason why the A group is called our representative elements is because their properties are pretty stable. Each of these elements has the same number of valence electrons, which is a super important thing. So all of these elements are in their columns because of their valence electrons. Valence electrons, the easy way to I've been up since 4:30 teaching. I'm so sorry, y'all. I stutter a lot. So the easy way to figure out how many valence electrons something has is by the family number. This first family is called the alkali metals. They all have 1 valence electron. The second family with the alkaline earth metals all have 2. The third family, or 3A family, has 3, 4, 5, 6. This dark blue family is called the halogens. They have 7. And this purple family is called the noble gases. They all have 8. The magic number in chemistry is 8. If you have 8 valence electrons, you are stable. You don't want to form any bonds with anybody. That makes you happy. Cool? The middle group right here, these are our transition metals. So the reason why we call them transition is because their charge or their valence electrons varies. It's hard to predict. So that's why we don't really talk about them too much in terms of valence electrons. Sorry, everyone. There are some exceptions. So for example, silver, which is number 47, which should be right about here, has 1 valence electron. Tin is in there somewhere. It's got 2. So there are a couple of exceptions to the rule, but most of them have varying charges, and they're all metals. The second way, so besides our periods and our groups, the periodic table is also organized by state. So whether it's solid, liquid, or gas, or if it's metal, non-metal, or metalloid. So if you have the slides, you have all of these images already, and I can definitely send you out the recording if I'm talking too fast. But just to show you, so this periodic table has all of our families highlighted, our families and their properties. This pink group right here is called the metalloids. The metalloids are a little bit unique. So everything underneath this, we call this the staircase. All of these guys over here are metals. The metalloids are the kind of like the separating point for these tannish and yellow elements. These are all non-metals. So sandwiched in between, you have the metalloids, which act kind of like a metal and kind of like a non-metal. So it's kind of a visual representation if you can remember where these are. Everything underneath the staircase is metallic. Everything above this staircase is a non-metal. So that really kind of helps in terms of identifying what is what. If you can just identify these 7-ish elements, separate them out for you. I will also note that this row right here is not on the periodic table, that it stops like at number 108, I think. These are all relatively new and radioactive isotopes. So on the periodic table that they're going to give you, these guys are not there. So don't be alarmed if these boxes are empty and cleared out. That is not everything that the periodic table can tell us, but we don't have time to go through the whole periodic table in an hour. That is something we teach students in 3 weeks. So in the email, I sent out a Praxis guide that I made. So I don't know if anybody got this book from ETS. If you have this book, the guide that I made you, I took the study samples that they had in this book and made a whole study guide. So don't feel like you need to buy this book, because I literally, so inside of it, like the very first thing is just like an overview of every topic that could be on the test. I took this topic list and made a gigantic study guide that's like 200 pages long. So I'm gonna send it out section by section based on how we're gonna cover things. But if you don't wanna spend the $50 for this book, you're basically gonna get it anyway. Okay, so just so you know, if you don't feel like buying this thing. But in the thing that I sent you was a whole breakdown of the periodic table. It goes over the families in depth, valence electrons. It'll talk about electron configurations, which I don't have time to teach, but it's definitely going to show up on the test. If you have questions about it, please email me. But I want to focus today mostly on how to identify protons, neutrons, and electrons, and how that makes atoms, isotopes, and ions. Are there any questions about the periodic table that people want answered now? Okay, I see some shaking heads no, and I see some people like, I'm okay. So real quick check for understanding. There are 4 elements on the screen: antimony, iodine, phosphorus, and chlorine. Which of the following would have the smallest atomic radius? So think about what we just talked about in terms of periods. Which element would have the smallest atomic radius? So just in case, let's see. I'm gonna quickly see if I can write on the screen real quick, just to make sure, so just in case people can't see the elements right off the bat. We're talking about antimony, iodine, phosphorus, and chlorine, those 4. Which one would have the smallest atomic radius? I see one answer in the chat, and I'm gonna give it a thumbs up. James, I think I saw you mouth something, but I'm not sure. So the answer that I'm seeing in the chat is chlorine, which is correct. Of all of these elements highlighted, chlorine is in the 3rd period, and it's farther to the right. So they get smaller as you move in this direction. So that means the smallest elements on the periodic table are up here, and the biggest are down here. Okay. So of these 4, the smallest in terms of radius would definitely be chlorine. Everybody okay? I don't know how to get rid of my annotations. Yes, I do. Wonderful, wonderful. So moving right along for the evening, again, I definitely want to respect our time, and it is going quickly. Let's talk about a couple more things that our periodic table can tell us. So if you look at the periodic table and you find an element, it will tell us some different information. So the letters are the chemical symbol. If you looked at sodium, which is number, let me show you. Why is my screen going backwards? There we go. So sodium is right here, number 11. If we were to blow this up a little bit, we would see that its number on the bottom is like 22.9, which is about 23. So the one way we sum this up is by writing it in what we call nuclear notation. Nuclear notation takes the mass of our element and puts it on top, and the atomic number on the bottom. A couple important things to remember. The mass is determined by what's in the nucleus. So we only have protons and neutrons in the nucleus of our atoms. We add those two together, we get our mass number. Electrons do not have very much mass at all, and they're located in the orbitals, so we don't count them in our mass number. It's only protons and neutrons. The atomic number, which is the top number on the periodic table, is the number of protons in an element. This is the only number that cannot change for any element. So the mass can change. This little symbol represents our charge, which means we changed electrons, but we can never change the number of protons. If we change the protons, then we have changed the element. So in sodium, I know that it has 11 protons because its atomic number is 11. If I know that its atomic number is 11 and its mass is 23, I can just subtract the atomic number from the mass number to find out how many neutrons it has. So 23 minus 11 would be 12, so that I know this sodium has 12 protons, 12 neutrons, and 11 protons. That's why its mass is 23. Again, this little plus sign, and sometimes it's a minus, it tells you the charge. So if we see a plus, that means my atom has lost an electron. Okay. Have a negative charge, protons have a positive charge. So if I lose an electron, that means I now have more positive than I do negative. So this would be a +1, which means I would have 10 electrons in this sodium versus 11 in a normal one. If this was a minus sign, then that means I have gained an electron. So I always tell my students, when we're trying to figure out the numbers of protons and electrons, if I see a plus, I want to subtract. If I see a minus, I want to add. It would be the opposite of the symbol. What we're really talking about when we look at these three numbers are the regular atoms, something called an ion, and something called an isotope. So our atoms are the normal boxes on the periodic table. They differ by their number of protons. If you want to make an ion, all you're doing is changing the number of electrons. So that means something has gained or lost electrons. To make an isotope, all you do is change the number of neutrons, which means you'll change the mass number. But either way, the protons must be the same for a particular atom. You give him his pacifier. He just had it. So putting it all together, if we looked at a chart like this, and we'll practice with this a little bit before we move on because this is kind of important in terms of chemistry. If I looked at an element like calcium, and let me get it. Okay. Calcium, anybody know the symbol for calcium off the top of their head?
Ca.
Yep, calcium is Ca. Okay. Calcium is Ca, its atomic number is 20. If I had a periodic table in front of me, if atomic number is 20, how many protons should it have?
20.
20. The protons and atomic number have to be the same. If it were neutral, so neutral means the positive and the negative equals out, how many electrons would it have?
20.
20. And for this one, how do we figure out the number of neutrons?
It's the mass, the atomic mass minus the atomic number.
Yep, or minus the protons, whichever way. So that means this one has 20 neutrons. So if we look down here where I have another calcium, the symbol still stays the same. The atomic number is still 20, but this is what we call an isotope. Again, when we make an isotope, the only thing we're going to change is the mass number. So for this calcium 42, its atomic mass isn't 40, its atomic mass is 42. Does it still have, how many protons does it have?
20.
20, because that can never change. How many electrons would this one have?
20.
20 as well.
20 as well, because the protons and electrons in a neutral atom still have to be the same. However, this time, how many neutrons are we looking at?
22.
22.
There you go. Y'all don't need me, for real. Now down here, we have an ion. So an ion looks like a regular calcium, but now we've got this guy up top. So in terms of our information, still got 20. We'll go back to our mass of 40 because they don't say any other number. We still know it has 20 protons because that can't change. But in an ion, are we changing our neutrons now or our electrons?
Electrons.
Electron.
Electrons. If we have a 2+ charge, what does that actually mean in terms of our electron number?
You'll have 18 electrons.
You'll have 18. 2+ means you lost 2 of your negative charge. So you're 2 more positive than you are negative. And then just like the first one, you'd still have 20. Really wanted to kind of talk about nuclear isotopes. That's going to be the focus of today, but I wanted to make sure we understood the difference between atoms, ions, and isotopes before I continued, because radioactive decay is going to play heavily on the isotopes. So again, just to review, because it's just super important to the fundamentals of chemistry to understand this piece right here. Atoms differ by your protons. So if you change the number of protons, you've changed the element completely. Ions differ by number of electrons. So that's when you get a charge. And when we talk about bonding, it's all about ions. And isotopes differ by the number of neutrons. So it's the same identity, it just has a different mass when you created an isotope. Now we're going to talk about radioactivity today. It's going to come up in a couple different areas on your test. So it'll come up in the physical science section for the things that we're going to talk about today. It will also come up in earth science because it'll talk about radioactive and carbon dating. So half-life will pop back up again. And it's also going to come back up in human impact. So they're going to talk about how do radioactive isotopes degrade and how do we contain those materials and how is it hazardous to people. So this is going to pop up a bunch of times. Here, before we move on to radioactivity, is a sample question from a release Praxis. It says the diagram above represents atoms, the number of protons, neutrons, and electrons, and each is indicated by the differently shaded circles. Which of the following are isotopes of the same element? So we just talked about isotopes. Which 2 elements are isotopes of one another? When you think you know, shout it out in the chat, and I want to know why. Let's justify it.
1 and 2.
Okay, so I hear 1 and 2. Does anybody agree?
Oh, wait. No, 1 and
1 and 3.
1 and 3.
I agree. So 1 and 2 can't be isotopes of each other because they have different numbers of protons. So that means this one, if it has 1 proton, will be hydrogen, and this one with its 2 protons would be helium. You're looking for elements that have the same number of protons. So 1 and 3 are both helium, but they have different numbers of neutrons. Therefore, 1 and 3 are isotopes of one another. If we wanted to write them in isotope notation, number 1, since we just said it's helium, and it's got a mass of 3, so that would be helium 3. And this number 3 right here would be helium, that's 4. It's got 2 protons, 2 neutrons. So in isotope notation, we write the mass number right next to our symbol. Another reason why I brought this up is because helium-4 is going to be essential to radioactive decay, which we're going to talk about in just a second. Questions for me? Am I talking too fast for anybody, or is my accent getting in the way for anyone? Because that happens sometimes. Okay, good. You guys are sweet. Appreciate it. All right. So helium-4, the isotope we were just talking about, can also be written in nuclear notation. In nuclear notation, you put the mass number, so that's protons and neutrons on top. atomic number on the bottom, and the symbol to the right. This guy is especially important because it is the symbol for alpha decay. In chemistry, in our NC standards, we teach our kids 3 different types of decay, even though there are more, but we just teach them alpha, beta, and gamma, and luckily those are just the 3 that the Praxis asked us about. When we say nuclear decay, it means that you have one parent element that is spontaneously getting rid of one or more of these isotopes, and when that happens, you have to change the mass and atomic number to create your new daughter. So it looks a little bit like this. In this top example, we have uranium-235 going through alpha decay. The arrow means decay, so it shows me that the uranium is letting go of an alpha particle, which is 4/2 He, and we've created thorium. The way you solve these, if you know an alpha particle is 4/2, you're going to subtract 4 from the top number, subtract 2 from the bottom number. That's why I have 231 and 90. And then 90 is going to be the element that I look for in the periodic table, which is thorium. Okay. Bonus. Anybody know who thorium is named after? A Norse god. He's in the Avengers.
You're kidding, really? Thor.
Yeah, Thor.
Right.
So thorium is named after Thor. That's a really fun trivia question that my students like. Or we could say Chris Hemsworth, because he's a man crush for a lot of people, me. Second, we have beta decay. So we have the same uranium-235 letting go of a beta particle. Alpha is 4/2 He. Beta looks like this symbol. So we have a 0 on top, a -1 on the bottom, and an E. A beta particle is the same thing as an electron. So that's why it has no mass, a -1 with its atomic number, and an E representing electron. Because beta particles have no mass, we don't change our mass number for our daughter product. And if you subtract a negative, that's the same thing as adding a positive. So we increase our atomic number by 1, which changes it to neptunium, which is named after Neptune. Last decay that the standards and the test ask you about is gamma. Gamma is different from alpha and beta because gamma is a wave. So we call this an alpha particle. This is a beta particle, but this is a gamma wave or gamma ray. Because it's not a particle, it has no mass and no atomic number. Excuse me. So if you see something changing, that means another particle has to come out. So this bottom one is actually not complete. We're missing something. If you look closely, what type of decay would actually complete the gamma decay problem? What changed right here? What's missing from the top number?
-4.
-4. So in log conservation of mass says you have to have the same amount of substances on both sides of the arrow. So if you see that there's a gamma particle gone, but there's still numbers changed, that means the top number is 4. The bottom number has changed by what?
2.
So in this case, let's pretend it's a 90 so that it can be a 2. So if it was 4/2, our symbol would be?
Helium, He.
He.
He for helium. And now it's complete. So the last thing I want to mention about our decays is that alpha and beta can never happen at the same time, but alpha and gamma can happen and beta and gamma can happen. Because gamma radiation is literally just a spontaneous release of energy. It's not releasing a particle. So it can happen with other decays, but alpha and beta cannot happen at the same time. Now, if anybody teaches high school level chem, you're gonna have, every now and then you will encounter some of the other decays, but these are the 3 that are assessed on the Praxis in the NC standards. Positron and neutron emission, all that stuff is not mentioned. So we can talk about it if you want to, but it's not covered on the test. So let's see what we know. Based on what we just reviewed, what do we have here? So we've got radon 220. in our nuclear notation up top. Which of the following results when the nucleus of the radon atom shown above emits an alpha particle? So if radon-220 goes through alpha decay, what would you get? Even if you didn't have a periodic table in front of you, what could you look at just to make sure? If you know alpha, alpha is what over what?
4/2.
So A.
A.
A. Now, if you wanted to double check, you would make sure that you looked at the periodic table to see that number 84 is actually polonium, and it is. I had to think about its name, sorry. But if you just look at the number, the only one that's 4/2 in the right direction is A. How we feeling? We okay?
Mm-hmm. Yes.
Can you repeat that one more time? I'm sorry.
Which part?
You said something, how you got the answer?
Okay, so because it said alpha right here at the bottom, I have to remember that an alpha particle is 4/2 He.
Oh.
There we go. Yeah, this is no easy way to write on the screen, so sorry this is so ugly. If it's 4/2, that means my top number is going to be -4, which would be 216. I'm going to take 2 from the bottom number, which would be 84. The only one with those correct numbers is A.
Oh, okay, duh.
There we go.
It just went over my head just a minute. Yeah.
So at the end of this, I'm going to give some tips and strategies. One of them is focus on your strengths. So for me, physics was not a strong point for me because I was not coming from science. So I focused more on chem and bio because that's where I was strongest to make sure my points were made up there and did physics last. So for some people in here, chemistry is going to be one of those things where you're like, this is not for me. Focus on the areas that you already know well and then come back to this part towards the end. That's one piece of advice I can give. And half-life is going to come up again in the earth science part because this is one of the tests that we use for radioactive dating. But half-life is the amount of time it takes for half a radioactive isotope to decay. So one of the major problems with nuclear isotopes and radioactive things is that it takes them a very, very long time to actually decay and go away. So when we do half-life problems, there is an equation, and I know some people said on their practice test they saw the equation come up, but because the Praxis is calculator free, I'm going to teach you a way to do it that does not involve a calculator necessarily. Okay, so this one says, if the half-life of a 50-gram sample is 3 years, then in 3 years, only 25 grams will remain. So that means every time you hit the half-life, the initial mass of your substance will get cut in half. So that means 3 years later, you would have 12.5 grams and so on and so forth until you eventually get to 0 grams. Okay. So when you want to set up a half-life problem, the easiest thing to do is to draw a T-chart. T-chart will look like a neater version of this. On the left, you can put time, you can put half-life, you can put whatever you want to. And over here, you can put HL or you could put X for your isotope, depending on what we're dealing with. Sometimes I like to list the actual radioactive isotope we're dealing with. And in this problem, it talks about nitrogen-16. So I'm going to put nitrogen-16 on this side. Also, when you set up your T-charts, the first number under time will be 0. Because that's your initial amount, is what you started with. My problem says, what is the half-life of a 100-gram sample of nitrogen-16 that decays to 12.5 grams in 21.6 seconds? So to figure this one out, I have to do a little bit of manipulation and a little bit of division. So if I use the information it gave me in the problem, it says that my initial sample was 100 grams. I want to cut that in half until I get to 12.5 grams, and then I'll deal with the other side. So half of 100 is 50 grams. half of 50 will be 25 grams, and then 12.5 grams down there at the bottom. Because half of 25 would be 12.5. Now, in the problem, it says that it took me 21.6 seconds to get to 12.5 grams, and it wants to know what's the half-life. So in a problem like this, all you have to do is count how many times that you divided it, and then divide your time by that number. So I had 1 half-life, 2 half-life, 3 half-lives. So to figure out what the half-life here is, I'm going to divide 21.6 by 3. So my half-life would be, what, 7.2? Yep. Yep, 7.2 seconds would be the half-life of this radioactive substance. Pardon my terrible handwriting on the screen. Questions on this one?
Are we always gonna divide by 3?
If you had gone further, so if it had you decay to 6.25 grams, then you'd be dividing by 4. So it's how many times you have cut the substance in half.
Okay, but we're always dividing it by something.
By something, unless it gives you the half-life, and then you'll be adding on that side. So I think I have one that looks, let me just,
Because I have a question, because I done seen some questions where it don't include the time. It just be like, what's the half-life of like the gram, but it don't say nothing about time.
like this, kind of like this one.
I think
This one's about time. This one's having you figure out what the half-life would be too.
okay. Then it may be more so that because it really don't. I might be saying it wrong.
That still has a time. This time is just years.
Yeah, usually half-life involves time. So they can either ask you what's the half-life, they can ask you how much of a substance remains after a certain amount of half-lives. That's like usually the two ways that they rephrase these type of questions. But you can solve all of them with the same T-chart. So this one right here says all isotopes of technetium are radioactive, but they have widely varying half-lives. If an 800-gram sample of technetium-99 decays to 100 grams in 639,000 years, I'm sorry, I'm missing something. There we go. What is its half-life? So you can set it up same way. I'm on screen. There we go. With my time, and I'm gonna put my substance, technetium-99, still put my 0. So we have an 800-gram sample. Cutting it in half. We go to 400 grams, then 200 grams. Goodness, my handwriting is terrible on here. And then lastly, 100 grams. And it says it took us 639,000 years to get there. So this one is similar to the last one where we're going to count how many times that's happened, which is 3, 1 half-life here, 2 half-lives, 3 half-lives. So again, this one we divide by 3, similar to the last one. And the half-life of this technetium is going to be what?
213,000.
Good. 213,000 years. Make sense? Okay. So let me see. Let me make sure I have the right thing up real quick. Sorry, Zoom is super complicated on my end. There we go. We'll do a little bit of practice together. Let me get the right problems pulled up. Tonight, I want to talk about some different types of reactions and talk about balancing equations. because I know it's on there a little bit. I heard it's more on the high school test, and I know people are saying only maybe 1 or 2 questions on the middle school for this concept. But I know there's probably a good deal more of this on the high school. One thing
today.
but it had kind of something about a double replacement reaction, you guys said, right?
Yeah, but I'm telling you, I think I had Chelsea's test from yesterday.
Yes, it had like a double replacement, and then that's when it started asking about, it had double replacement, and then it had oxidation on there too.
Yes.
Okay, so I'm going to send you guys something. So oxidation states have to do with their charges. So their charge number is the same as their oxidation state. When you have double replacement reactions, how things switch, you have to do what we call a swap, drop, and chop in our classroom. And that means you swap the oxidation numbers over to the other side and drop them down at the bottom.
So you drop the coefficients?
Yeah, so the oxidation states are usually written as exponents. So you swap them and make them subscripts.
Subscripts. Got you.
And so that could have been what they were talking about, like, what is this thing's oxidation state? It's asking you what is its charge, essentially. So when I send out the recap tonight or tomorrow, I'll add some information about like calculating the oxidation state, but it's really just, you just need to know about its location on the periodic table.
Gotcha. Okay.
So if you was like doing something with lithium, like the charge on it would be 1 or something?
1+, and that will be its oxidation number.
Why
does lithium before it gets swapped?
Yes, lithium has a 1+ charge because it has 1 valence electron. So it's going to get rid of its 1, making it a 1+.
Gotcha.
Okay, when it loses 1, it's a positive.
So when you're combining them together, so you see how in combination has A plus B, and then together is AB. It has something like sulfur and oxygen, and the answer choice it had like SO, S2O, SO2, and I forgot.
I had your test today.
So let's look at something like that.
Yes.
How did you do?
Goodness, my grandma laughing at you.
How did you do?
Let's put it this way. If it had been me studying and these group things, I would have done worse. I promise you.
Okay.
It wasn't good, but it wasn't bad, but still. Oof.
So when you have something like sulfur and oxygen, sulfur sulfur does not have a 2+ charge. I'm sorry, I'm trying to do this off the top of my head. I think sulfur has a 4 charge. Let me double check before I tell y'all the wrong number. I think sulfur's a 4 though. Highest charge that you can really have is like a 6, but you don't really see 6 often.
Right. I'm like 1, 2s, and where they're on the bottom.
It was a 4.
I think sulfur's in the 14th family, which would make it a 4. It would be a 4.
Yeah.
So let me just redo it. So if sulfur is a 4+ and oxygen is a 2-, when you swap, drop, and chop this thing, you're going to take the 2 from oxygen and you put it down at the bottom of sulfur. You take the 4 from sulfur and you put it at the bottom of oxygen. So you end up with S2O4. Now, when you chop this down, chop means reduced. So 2 and 4 can both be divided by 2. Like if you had, if you had 2/4 as a fraction, that would be the same as saying
1/2.
1/2. So S2O4 is actually SO2.
That's what I picked. So I was like, I've usually seen it together like SO2. So
that's sulfite. That's also the name. SO2 is also sulfite ion.
So that would be the oxidation.
The oxidation would be up here. These plus and minus things those are the oxidation numbers.
Okay.
And those are determined by their position on the periodic table. So what I'll send out tonight is also like a labeled one that has all their oxidation numbers and charges. You don't have to memorize them, but if you know that the whole first column is a 1+, the whole second column is a 2+, it actually follows a pattern when you look at the whole thing.
Okay.
So like the 13th column is a 3+, the 14th column is 4+ or minus, because they either way, it depends on what they're paired with. The 15th column is 3-. They have 5 valence electrons. They need 3 more to get to 8. So they would have a 3- charge. 16th would have a 2 minus, 17th has a 1 minus. The 18th family is a 0. They're noble gases. They have 8 electrons. They don't want any more. So their oxidation number is 0.
So they get rid of their family members.
Mm-hmm.
So that isn't like the 4 and the 5. You can be positive or negatively charged.
For the 14th family, you could be positive or negative.
Okay, I remember that now.
That's the
So-
halogen.
The halogens are the 17th. That's the 1 minus family.
So who's the 14th?
14th, they don't really have a name. That has sulfur on the top, so they're kind of just named like the sulfur family.
Oh,
The only ones that have names, the first is the alkaline metals. The second family is the alkaline earth metals. Then all the way on the other side with the 17th family, that's the halogens, and the 18th family is the noble gases.
Yep.
Those are the 4 major names that we have in terms of the families.
Okay.
So let's look at balancing real quick. I don't think your test will really have you like identify equations by name, but just in case to run through. So a synthesis is when you have 2 elements that become 1. Decomposition is the opposite, so 1 that falls apart into 2. In a single replacement relationship, you have 1 element that bumps another one out of the compound, so somebody ends up lonely and alone. In a double replacement, everybody has swapped their partner, and the key in combustion is to look at the products. So whenever you produce carbon dioxide and water, you have a combustion reaction, but it must be carbon dioxide and water. I'm sorry about that. That thing's annoying. It must be carbon dioxide and water in order for it to be a combustion reaction. If it's like carbon and water, it's still single replacement or double replacement. But if it's CO2 and H2O, you have produced a carbon dioxide. Produced a combustion reaction. Okay. So real quick, in this first one, what type of reaction would that be? What do we think?
A double displacement.
Mm-hmm.
Yeah.
Sodium was with phosphate, potassium is with hydroxide. Now sodium is with hydroxide and potassium is with phosphate, making it a double displacement or double replacement, whichever word is fine. So the second one is similar. It would also be
swap places, so they were swinging.
They're swingers. The swingers. If anybody wasn't on the first time, we told my students to think of them like relationships where everybody has a new partner. And so they're like, oh, that's the swinger relationship. And I was like, whatever y'all say.
I remember that one.
So what's happening with our magnesium chloride and lithium carbonate? What happens on this side?
They're swapping.
Same thing.
Good. So everybody now has a new partner. They've swung away. We also have a double replacement reaction. What about down here in the third one?
Combustion.
Yeah, because of the water and the CO2.
Well, yeah, CO2 and water.
You guys got it. Let's just do one more.
Combustion, they always have to have the
Yes.
no matter what.
Yep.
Will this be
A single deflected spot.
Yeah, this one is single. So lead was by itself and iron was with the sulfate. Lead has taken the place of iron and kicked iron to the curb. So my kids said this was Khloe Kardashian and Jordan Thompson and Jordan Woods. That's what my kids said this relationship is. Right. Khloe got left by herself.
Angelina Jolie. Okay.
That's the one I used to put in there was Angelina Jolie and Brett and Jennifer Aniston, and like they used to switch, but my kids were like, who are these people? I was like, okay.
That was before the Kardashian.
They made me feel old, and I'm only 28. They'd be like, Miss Fields, that's wrong.
Are you only a year older than me?
Did someone say I'm older than them?
No, I said you're only a year older than me.
Okay.
Well, I'll be 28 this year.
Ooh,
I'm 29 in August.
I love all of y'all. Y'all don't want to know.
We love you dearly, Miss Simmons. All right, so let's take a look at balancing real quick. So when we balance equations, what you want to do is first take inventory of all of our elements. So when we count elements, we use the subscripts to help us figure out how many of that element we have. Now, a subscript is only attached to the element right directly in front of it. So this Lord Jesus, sorry. This 4 goes with the H, this 2 goes with that chlorine, this 4 goes with that chlorine, right? It doesn't apply to the whole molecule. So when we want to balance this, the first thing we want to do is take account of how many of each element we have, and we count the arrow, we divide it by the arrow. So if they're on the same side of the arrow, they count together. Our reactant side here, I would have 1 carbon, 4 hydrogens, and 2 chlorines. On my product side, I have 1 carbon, which is okay because there's 1 on the other side. So that's balanced right now. I have 4 chlorines, but you have to be careful because remember, this chlorine still counts with this one over here. So I actually have 5 chlorines on that side in total and 1 hydrogen. So I know it's not balanced right now because I have an uneven number of chlorines and an uneven number of hydrogens on the right side. So to balance it out, what I would have to do is add in something called coefficients. Coefficients multiply against the entire molecule. So a couple tips for you. If you were going to balance this equation, you would definitely want to start with this hydrogen before you started messing around with the chlorines. So if I put a 4 here, that now gives me 4 hydrogens, which is what I wanted because I had 4 hydrogens here. And that will give me 4 plus 4 chlorines, because 4 times 1 would be 4. So on the right side, I now have 8 chlorines, which is an easier number for me to deal with. That means to get 8 chlorines on the left side, I have to give it a coefficient of 4. 4 times 2 is 8, and now this whole thing is balanced. Balancing is one of those things that some people need a lot more practice on, and some people get relatively easy. So if it comes later to you, that's okay. This is one of those things in chemistry that I really didn't learn well till my 3rd year teaching it, if I can be honest. So this one will come with time. We'll practice a couple of them, and then for the practice worksheet I have, I'll send it off for you. And if you want to work on it on your own, just because it's already 7:24, and I know some people have things to do. Bryson done got dressed. He ready to go. Look at that. What is it? Is it Thursday? You going to a live after 5? Where you going?
Oh, God.
Shauna, will you put the answers up for that half-life sheet?
Yes, I will make a whole worksheet for it and put the answers up because I don't have one yet, but I can do it tonight.
Okay, thank you.
Is that a glucose molecule?
With the C6H12O6, yes.
Yeah. Cool.
So if I want to balance this guy, I've got CO2 plus H2O yields C6H12O6 and O2. This one's going to require a little bit of back and forth, though, because we have a bunch of things all over the place. But I figured I would give us I give us a little harder one to start with. So if we list it all out, this is how I would list it. I like to list my oxygen twice, so I remember that there's 2 of them over there. I have 1 carbon, 2 oxygens, another 1 oxygen right here, and 2 hydrogens. So I want to remember that there's 3 oxygens in total on the left side right now. Same thing on the other side. And this is just a habit of mine where I list them out on the same on both sides just so I can easily see my numbers. You can list it however you want to, but I just like to keep the order the same so I can keep it neat. But I see that I have 6 carbons, 6 oxygens, 2 oxygens, and 12 hydrogens. Okay, does everybody see where I get those numbers from?
Yes.
Okay, so that means I have 8 over here. Now, a lot of people, when they start balancing equations, are tempted to try to fix those oxygens first. As a pro tip, you should leave them till the end. Fix everything else that you can fix first, and usually that will actually fix your oxygens for you or make it easier for you to deal with. So for us, let's try to balance the carbon and hydrogens first and see what that does to our oxygens. So if I have 6 carbons here, how can I make 6 carbons on this side?
If you make that 6, wouldn't that make it 12?
Put a 6 coefficient.
Yes.
So that makes that a 6, and that does make this a 12, which is okay for now.
Because you can fix the rest later.
So my carbons are good. Let's make my hydrogens good. So I've got 12 hydrogens here, but only 2. So what do I need a coefficient of here?
6.
A 12. Oh, 6.
Because you want to make it
Oh,
12. So you have to multiply.
Yeah.
So we got 12. And now we have another 6 oxygens here. So in total, what's 12 plus 6? Because remember, they count together.
18.
18.
So we have 18 oxygens that we have to deal with now that our carbons and our hydrogens are all fixed. Now be careful on this side. Remember that there's 6 oxygens here, so you don't really want to mess with this one. We're not going to mess with it. We still want to get to 18, but I'm not going to mess with this 6 because that'll throw off my carbon and my hydrogen, and I don't want to mess with those anymore. So the best way to handle this one is, so you've got 18 that you need, but we've already used 6. So what's 18 minus 6?
12.
12. So now you want to make this other oxygen a 12. So what number do we need?
6.
6.
And we're going to rebuke that number in the name of Jesus.
I know that's right. Come on now.
But that does give us the 18 that we need, and now the equation is balanced.
I just saw like 3 6s.
Yep. So we prayed against that.